This is my video lab report for Lab 3 in Physics 1, in which we explored black holes and orbits in GlowScript. There were two parts to this lab. Part 1 was called Finding the Mass of the Black Hole, and the purpose of Part 1 was to use motion data to determine the mass of the black hole by analyzing a star's orbit and applying Newton's laws of motion and gravity. Part 2 was called Orbit and Don't Crash, and the purpose of the Part 2 is to simulate the gravitational interactions between a planet, its moon, and a spaceship to determine the initial velocity needed for a spaceship to achieve a stable figure-8 orbit influenced by both the planet and the moon. The first relevant physics principle for this lab is Newton's law of universal gravitation, given by the force of gravity is equal to the constant g times the magnitude of object times the mass of object 1 multiplied by the mass of object 2 divided by the distance between them squared. In this case, you can tell object M1 is exerting force of gravity 1 towards M2, and F2 is exhibiting force of gravity of itself towards M1, and these forces are equal in magnitude but opposite in direction. Other physics principles that are relevant to this lab are the momentum principle, in which momentum is equal to mass times velocity, but then the net force can be given by the change in momentum over the change in time. Additionally, velocity and position update formulas, which we covered in both Lab 1 and Lab 2, are also relevant again for this lab. And then parallel and perpendicular forces are something new that are relevant to this lab, in which the net perpendicular force changes the direction of an object's motion, while the F net parallel force changes the magnitude of an object's motion. The key takeaways from this lab were the mass of the black hole I found to be 1.39 times 10 to the 34th. I found the initial velocity to be negative 4.3 times 10 to the 4th in the x direction, 4 times 10 to the 5th in the y direction, and 0 in the z direction. Some key assumptions I had to make during this lab were that gravity is the only force acting on the objects are point masses, the black hole and planet don't move, the time step between data points is constant, Newton's law of gravitation and Newton's second law are valid throughout, and the system is isolated. This was my coding for part 1. The system was the star and the surroundings were the black hole. I had initial conditions, and then I had to edit the calculation loop. I also had to insert my email in order to get a specific mass for my lab specifically. Here we use the momentum principle to first find the mass, and then we were able to calculate F net through calculating F net parallel and F net perpendicular individually. The mass of the black hole, as seen through the data collected by taking the orbit, was 1.39 times 10 to the 34th. In part 2, our system was our spaceship and our surroundings were our planet and our moon. And in this case, we had to use trial and error to calculate a valid velocity that would allow the spaceship to orbit the planet and the moon without intersecting or crashing into either orbits. And what we had to do was we had to find FNet on the moon and FNet on the spaceship using coding through GlowScript. And these are the relevance coding that we used in this lab. For my result for part 2, the spaceship's trajectory gets really close to the moon's orbit, but it does not intersect at this initial velocity in my computational model. However, I was not able to achieve a stable figure-8 orbit for part 2. Potential sources of error I think might have accounted for this is definitely round-off error. There was as we were doing GlowScript code, especially with regards to part 1, it was calculating multiple masses throughout. However, each one was rounded, so you lose a sense of precision in those calculations. Additionally, we assumed many physical omissions throughout this lab, such as that we didn't regard anything that wasn't the force of gravity. We just ignored. And then also we always assumed point mass and fixed center assumptions, so something wasn't moving, and we weren't calculating its velocity update for every object in our systems. And we also had trial and error. We used trial and error to find initial velocity. Now for our discussion part of this lab, the what if and what does it mean? So our what if question was, how does the net force and its parallel and perpendicular components differ from the change in momentum and its parallel and perpendicular components? Well, according to Newton's second law, the F net is equal to the change in momentum of the change in time. The parallel component of both vectors changes the magnitude of the object's momentum, while the perpendicular changes only its direction. In practice, they may vary slightly due to approximations in how velocity and acceleration are calculated, and we can also use the change in momentum over the change in time in place of F net for this lab, since we can solve for mass using change in momentum over change in time, while F net requires the mass to be already known. And then for our what does it mean, if you wanted to predict the motion of the entire system in, say, part 2, what would you need to include in your computational model? Well, we'd have to consider all bodies as dynamic masses instead of point masses, and the body would need to include all the gravitational forces between the planet, moon, and spaceship, along with each object's mass, position, and velocity, so they can all respond to one another's motion. We'd have to use Newton's laws. Their positions and velocities should update over time, and the planet's gravity would dominate in this model since it has the largest mass and the force of gravity is directly proportional to mass. Thank you. This is my video lab report for Lab